Hello class. This video is now going to address when we look at molecules, how are we going to determine if the hydrogens are equivalent or not? And so there's going to be two strategies that I'm going to share with you. The first is using the chemical distinction test. That is one way to figure out if hydrogens are equivalent or not. And then the second way is molecular symmetry. So what we have here on the slide is the rules on how to apply and use the chemical distinction test. I'm not going to read this to you. I'm going to go through examples that show you how to use it. And so this slide right here is for your reference. So you can go back and read it. This right here is telling us that there's going to be a difference between enantiotopic hydrogens and diastereotopic hydrogens. So just like we learned in Organic Chemistry 1, we've learned about enantiomers and we learned about diastereomers. So now we can look at individual hydrogens and give them this label of enantiotopic or diastereotopic. Now, when hydrogens are enantiotopic, they are going to be equivalent except when the molecule is in a chiral environment. So what does that mean? Like if you're trying to purify a compound and you use a chiral column, then they're not going to be equivalent. Okay, the chiral environment is basically the experiment that you're doing. So when we're looking at molecules and asking the question, are they equivalent or not, or determining if they're enantiotopic or diastereotopic, always assume that you are not in a chiral environment unless I specifically tell you. So if I show you a molecule and I'm asking, are these hydrogens are equivalent, and you find out that they're enantiotopic, you would be like, yes, they are equivalent because they're enantiotopic, because you're just assuming that it is not in a chiral environment. Okay? So enantiotopic hydrogens are equivalent unless specified in the problem that they are in a chiral environment. If they are in a chiral environment, then they are not equivalent. The next type of hydrogen is a diastereotopic hydrogen. Those hydrogens are always non-equivalent. So, best to go through some examples so you can see what I mean by enantiotopic and diastereotopic, okay? So let's go through this example that we've seen before. Benzene. We know that all these hydrogens, all 6 of them, are equivalent. And when they're all equivalent, we can use another definition, homotopic hydrogens. So we are going to use the chemical distinction test to show you that these hydrogens are equivalent. So I'm going to go to workbook here. So let's draw ourselves benzene. Okay, I'm going to draw in all the hydrogens here. Now, if you were given this molecule, how do you know the hydrogens are homotopic? Well, the replacement test says, chemically distinctive. So right here, the chemical distinction test is one way to use it, or the replacement test. I use those interchangeably. Okay, so the replacement test says we take our molecule of interest and we have to ask ourselves a question. And it always involves 2 sets of hydrogens. So my question could be, hey, is this hydrogen circled in blue and this hydrogen circled in green, are they equivalent or not? Now, in order to answer that question, you will take that molecule and redraw it. Okay. and you're going to take the blue hydrogen and replace it with an X, and all the other hydrogens remain the same. And then you're going to draw the exact same molecule on the right, draw it all over again, but this time replacing the green hydrogen with an X. Whoops. Like this. So now we have two molecules. Okay? So we can maybe circle that blue and circle that green. And now we ask ourselves, what is the relationship between these two molecules? And so you can take these two molecules, I'll say that's molecule A and that's molecule B. And you can take either one, A or B, and you can flip them around, rotate them in any which way to see the relationship between these two molecules. Now look at molecule B. What if I took molecule B and just rotated it? Okay. So if I took molecule B and I rotated it and I redraw it, so let's draw it right here. So I'm going to take molecule B, I'm going to take it and rotate it. Okay. And then I draw what that looks like. So the X is now there. So that molecule right there is still B, it's just been rotated. Okay, so we can circle that in green. So if I take molecule B, let's grab it here, and I take it and put it next to A. Do you see how I can overlay it perfectly? What word is that in organic chemistry when it can overlay perfectly? It's superimposable. Molecule B here is perfectly superimposable. And every hydrogen matches. You can see that if we just draw it here, this X aligns perfectly with that hydrogen with that one, and so forth, right? Everything matches, perfectly superimposable. When that happens, then the original question was, what is the relationship between these two? Is that they are exactly the same. So those hydrogens are homotopic. So they are equivalent, which means that they are going to give us one signal. Now you could do the same analysis and you will get the same answer. What if your question was, what is the relationship between that hydrogen and that hydrogen? If you go through this replacement test, you will see that those are equivalent as well. Those are homotopic, giving us one signal. And if you did this for every single hydrogen and in every single combination, you would see that it gives us one distinct signal because all 6 of those protons are equivalent. So that is the replacement test. That's one example. Let's do another example here. What about this guy, propionic acid? We've already seen that there's 2 signals because this guy and that guy are in chemically distinct chemical environments, and that's relatively easy to see because they're attached to such different groups. But it's always good to make sure that we can do it with the chemical or the replacement test. Okay, so let's do that. Go to the whiteboard here. So if I draw this molecule out, there it is. So the replacement test says, well, hey, we are asking the question, what is the relationship between those two? So we draw out the molecule, but replace one of the hydrogens with an X. So we'll replace that one first. Okay. And then draw the second one. And replace this hydrogen right here with an X. Okay. And now what I do is I say, hey, that's A and that's B. And then I can take either one of them and flip them and rotate them in any which way to see if they are superimposable or not. And you can clearly see that if I took B right here and try to superimpose it, you can see it doesn't match up. Doesn't match up at all because where this hydrogen is, there's an X over there. So that is not superimposable. So what if I took this molecule and rotated it, right? And flipped it 180 degrees. Would that help? Well, we could redraw it. We could take B and take this molecule right here and just flip it 180 degrees. What would that look like? And I redraw it like this. Okay. So is that superimposable? If I pick it up? No. It is just not superimposable. So when it's not superimposable like that, that tells us that those two hydrogens in question, this one and that one, are not equivalent. Those two protons, we could consider them constitutional isomers. Scratch that. So they are not in the same chemical environment because the replacement test shows that it's not superimposable. Okay? So they are not equivalent. Let's look at this problem here. Let's ask ourselves, what is the relationship between those two hydrogens? Are those two hydrogens going to give us one signal or two signals? Okay, so that's the question. So we need to know what they are, and we have to do the replacement test to figure that out. So our molecule, let's redraw our molecule. So we have a wedge there, H and H. Okay, so our question is, what is the relationship between those two hydrogens? So we redraw it, do the replacement test, and it doesn't matter which one you replace. I'm going to replace the one on the dash. Okay. And then on the right side, I redraw the molecule and replace the other hydrogen with an X. Okay. Now we have those two hydrogens, or those two molecules now to compare. What are their relationships between those two? Okay, so I can put little verses there. So what we have here is A and B. What is the relationship? Well, if I take B, can it superimpose? No, it can't. Because you clearly see that this hydrogen right here is on a dash, and on the dash over here, there's an X. It's not superimposable. So what if I took B and rotated it 180 degrees? So what would that look like? If I rotate it 180 degrees, we would have a molecule that looks like this. All right. So our X would go there, and our hydrogen, no, sorry, our X would go there, and our hydrogen would go there. Now this molecule that I just drew is still B. It's just been rotated 180 degrees. Okay? Now if I take that, does it superimpose? No. The X and the hydrogens, they're both wedges and dashes, respectively. So that superimposes, but now what's the problem? The bromines aren't superimposable. Okay? But what is the relationship, though? If you take put A down here, and you have B, what do we have? Do you see how we have a mirror plane? There's a mirror image of the two. So this is A, and that is still B. Okay. But what's the relationship? They are mirror images, but they are not superimposable. So by definition, what is that? That is the definition of an enantiomer. Enantiomers are molecules that are mirror images of one another, which are not superimposable. So that means that these two hydrogens right here are enantiotopic, hence they are going to be equivalent. So those two protons right there are going to give us one signal in the NMR. So those right there are called methylene hydrogens. Remember in previous videos I talked about methyl and methylenes and methine hydrogens? And in this particular example, those methylene hydrogens are equivalent because they are enantiotopic. Okay. Now, let's change it up a bit and let's put a alcohol group right there. And now let's ask ourselves the exact same question. Are those two hydrogens in blue equivalent or not? How many signals will they give? Well, we go back to the replacement test. Let's make sure we have everything drawn correctly though. There's going to be an alcohol there and an alcohol here. So when you look at A and B, you can clearly see that they are not superimposable because the X's and the hydrogens don't match up. So what if we take B and flip it around? Now if I flip B around 180 degrees, so I'm going to take this molecule right here and rotate it 180 degrees. What's that molecule going to look like now? Well, this alcohol group right here is now going to be right here. It's still going to be right there, but the orientation is now a dash. And on A, we still have the alcohol group right there because we didn't rotate A. Now, what is the relationship now between A and B? Well, they are not mirror images of one another, and they are not superimposable. What definition is that? When you have molecules that are not mirror images, not superimposable, those are diastereomers. So these two molecules right here are diastereomers, which then means that these two hydrogens right here are diastereotopic, which means they're not equivalent. So that means this hydrogen right here is going to give one signal, and this hydrogen is going to give a second signal. So these two protons right there are going to give each its very own signal because they are diastereotopic. Okay. Now, the next trick that you can use is molecular symmetry. So this molecule that I'm showing right here on the slide is the same molecule that we've been working with previously. It's this guy. Let's clean this up a bit. Okay. So this molecule right here is the exact same molecule on the slide. It's just the wedge was HA and the dash was HB. Okay. Now if we take that molecule circled in yellow, okay, it's in the plane. If we take it and rotate it 90 degrees and look at it down this angle here, that's what we see on this slide. If you can take a molecule and look and see a plane that's exactly the same on both sides, then that means those two protons are equivalent. So, for example, we are asking the question, is this HA and HB? Are they equivalent or not? Well, you take the molecule, orient it, and see if you can split it right down the middle, and everything's exactly the same. So you can see that there's a hydrogen on the left side and a hydrogen on the right side of the plane. We see the bromine, the carbon chain is in the plane. So there is a mirror image on each half of this molecule. Because there's a mirror half or a mirror image that are exactly the same, that means those two hydrogens are equivalent. So this is another way of answering that question of if hydrogens are equivalent or not. You don't necessarily have to do the replacement test if you can see it. Okay. Now, let's do that mirror image thing with this molecule when we made that minor adjustment by putting out the alcohol group on it. Now, are HA and HB equivalent? Well, we already know the answer. They're not. They're diastereotopic. But if we try to use the symmetry method, what would we have to draw in to this little slide here? We would have a wedged OH right there. Now, do you see how there's no plane of symmetry anymore? Because this side of the plane has a hydrogen and an OH, whereas this side of the plane only has the hydrogen. So each half is not identical. So because each side is not identical, we can say that these two hydrogens are not equivalent, that they're diastereotopic.